All right, ladies and gentlemen, you should have out your note packet. You should also have it open to page 3. You should have a calculator. And remember, I will go over the slide and then I will give you some time to write and then we'll point out the important parts of it. Okay, so we are starting where it says neutralization reactions in your notes. Okay, so a neutralization reaction is the reaction of an acid with a base to form a salt and water. The resulting solution is not necessarily neutral though. And so an example of it would be HCl plus NaOH yields NaCl and H2O. So HCl is hydrochloric acid, and the hydrogen of the hydrochloric acid will combine with the hydroxide of sodium hydroxide. So when you get those two together, then you look at hydrogen and hydroxide. You do your crisscross like you normally would, and you end up with HOH, which can also be written as H2O. Then we can also take the Na and the Cl. We always write the cation first. So Na is a positive 1 and Cl is a minus 1. I got those charges from the periodic table, which you probably should have that out too, by the way. And so then when you do the crisscross of these, you end up with NaCl. So that's your salt. All right. So again, you can just kind of write that as an example. Take a little bit of time here to write. Okay. So I would be writing that it is, and remember I write reaction as rxn, and I would say acid plus base, and then I'd say equals salt and water. And then I would probably just write this example, although we're going to do quite a few more examples. So, all right. So then let's say I have H2SO4 and NaOH. You can write this either underneath neutralization reactions or in the info /example section. So I would take the H from the sulfuric acid and the OH from the sodium hydroxide. That would create my water. So I'd end up with water on one side or on the as a product. Then I would take my Na from my sodium hydroxide and my SO4, which is sulfate, from my acid. Na is a positive 1. Sulfate is SO4, and it's a minus 2 if you look it up on the back of your periodic table. It's a polyatomic ion. So then when we do our crisscross, that 2 comes down, and I now have Na2SO4. Okay, so those would be my products. I would write those here. Now the issue is I need to balance it. I am required to balance these chemical equations. So yeah, we are going back to some of the things like writing compound formulas and balancing reactions. This is really just a specialized double replacement reaction if you think about it. Okay, so I have 2 hydrogens here and I have 1 hydrogen here. So, hydrogens might not be our best one to balance first. Let's look maybe at sodiums. Sodium's Na, and I have 2 of them over here. So I'm going to need 2 on this side as well. So I put a 2 there. Now that makes me have 4 hydrogens. So then I could put a 2 there in front of that. That would give me 4 hydrogens. That gives me 2 oxygens there. And that's 2 oxygens there, and then I have 4 oxygens here. So yeah, now I'm balanced. Okay, so let's look at acetic acid and potassium hydroxide. So again, we take the hydrogen from our acid and the hydroxide from our base, and that would give us water. And then we take the cation of our base, which is our positive ion, which would be potassium, and our negative ion of our acid, which would be our acetate. And so potassium is a +1 from the periodic table, and acetate's a -1. And so then we would crisscross those down, and we would end up with KC2H3O2. Then we would be able to write those as our products, and then we would need to check if it's balanced. So 1H, 1H, 1OH, 1OH, 1K, 1K, 1C2H3O2. We are good to go. So then let's do one more. H3PO4, which is phosphoric acid, plus sodium hydroxide. So again, I take my hydrogen and my hydroxide and create water. And then I take my sodium and my phosphate. Sodium's a +1, phosphate's PO4 with a -3 charge off your periodic table. So when I crisscross it down, all right, so those would be my products. Take a little bit right now and go ahead and balance that. Start with Na. Hopefully you put a 3 there and a 3 there. All right. So that should be all of the examples that we're going to do, but let's add some more information. So you can either, again, write this underneath neutralization reactions or info \examples. Now, neutralization reactions are exothermic. Okay, if you remember, exothermic means that heat is going to, or heat or energy is going to be written as a product, so it gives off energy, and it's spontaneous, meaning it happens without anything else causing it to happen. All right, so that should finish those top two areas on your third page, and we're now going to move to titrations. Okay, titrations are something we are going to do in class. We actually are going to do a lab on them next week. And titrations are a process of adding a substance of known concentration, which is known as your standard solution or titrant. You could also just call it titrate, to a substance of unknown concentration, which is known as your analyte, until the substance of unknown concentration is completely reacted. So there's a few vocabulary words. This goes underneath titrations in your notes. And I'm going to give you just a little bit of time to decide what you think you might want to write. So I probably would have written process of adding known concentration, which I would have written as titrate or titrant, to unknown concentration. I would have written analyte until completely reacted. That would have been what I wrote for this definition. So process of adding known concentration or a titrant to unknown concentration, an analyte, until completely reacted. Now, still underneath the titration section, indicators are going to be used to determine what's called the equivalence point. This will be a change in color of your analyte, and it will end the reaction. It will symbolize the end of the reaction. This specific point, when the indicator changes color, is known as the end point. We also use an instrument called a burette for when we do titrations. This is actually a picture of an Erlenmeyer flask. Okay, this is a picture of a burette right here at the top. Oh, where did my, I don't know where it went. Oh, there it is. Okay, so the burette is up here. This is it right here. Okay, but I'll go back. Again, indicators help us determine the equivalence point. The reason it's called an equivalence point is because the hydrogen ions equal the hydroxide ions at this point. That's why it's a neutralization reaction. Let's see if I can change that color. Change it to yellow. So this is when the hydrogen ions are equal to the hydroxide ions. Okay. It's not necessarily 7, but it is when those values are going to be equal. So again, this point is known as your end point because that's when the titration should stop. And a burette is one of the instruments that we will use. So indicators, equivalence point, equals, change in color, and end of the reaction, which means that it's the end point. And then I would write the burette, word for word. Now, like I said, a burette can be spelt with 2 T's or 1 T, so you see it written here with 2 T's and an E. Here's the same definition that I just had on the previous screen. Okay, this is the burette right here, and it has our titrate in it. Titrate. I am like not spelling that right. So it's not going to let me do that. So let me just go up here and do that. This is the titrant. Excuse me. That's there. And this solution in our Erlenmeyer flask is known as our analyte. You guys actually are going to do a titration lab, but you're also going to do a titration practical. And I'll talk more about that. All right. So acid-base neutralization and stoichiometry goes underneath your example of titrations. What it is we can actually use a balanced neutralization equation to find concentrations of acids or bases that are titrated. We can use dimensional analysis or stoichiometry or a formula to solve these problems. This isn't really the formula I like to use because it's more, this is more talking a little bit more about it as normality. So I'd really like to show you more as using a mole to mole ratio. That's why I have stoichiometry on here instead. Okay, so really underneath titrations, I would just write you can use stoichiometry from a balanced neutralization equation to find concentrations. So we can use stoichiometry
from balanced neutralization equations to find concentrations. Okay? So that goes underneath your titrations area. We're going to do, I think, 2 or 3 examples. And you have an example section for us to do this in. So just keep it in mind that you're going to do 3 of these. And you're going to need your calculator. So, what's the concentration of a 50 milliliter NaOH solution? And let me see if I can switch colors a little bit again. Let's see if it does. Okay, that is neutralized by 30 milliliters of 0.5 molar HCl. So I'm going to end up taking 30 milliliters of acid out of my burette. It'll get added to my sodium hydroxide solution, which has an indicator in it. And I will have had 50 milliliters in my Erlenmeyer flask. So I'm going to start first with the balanced chemical equation. So I'm going to start with HCl plus NaOH yields. Now I'm going to get NaCl and H2O or HOH. That's balanced, so I can go from there. So you're always going to start with your known values. So I have 30 milliliters of this, and it is a 0.500 molarity. Then I have 50 milliliters of this, and I'm looking for its molarity or concentration. Okay, so molarity, remember, is really just moles over liters. So you're going to start with your 30 milliliters of HCl. First things you have to do is change it from milliliters to liters. We know there's 1,000 milliliters for every 1 liter. Then we know the molarity. Well, molarity is 0.500 moles of HCl for every 1 liter of HCl. That's molarity, remember, is moles per liter. Well, now I've gotten it into moles of HCl. Well, I want to talk about NaOH, though. That's what I'm actually looking for. So I want to use my mole to mole ratio. Well, there's 1 mole of this for every 1 mole of this. So 1 mole of HCl is 1 mole of NaOH. Really, this is review information with stoichiometry. So you're going to end up with moles of NaOH. And hopefully you've got your calculator out and you're doing some calculations here. And I want you to have a number that you're going to write right there. Once you write that number there, that's the number of moles. But we don't want moles. We actually want concentration, which means I need to do moles over liters. So now I'm going to divide this by this 50 milliliters, but I'm going to change it to liters. So that will be 0.050 liters. Because we'll move our decimal over when we divide by 1,000. 1, 2, 3. So that would be 0.05 liters. Now, when you get that answer, that's going to be your concentration. And your answer should have 3 significant digits and be labeled as molarity. So I'm going to give you just a minute to go ahead and do that calculation real quickly in your calculator, and then we're going to move on. Now the second example that we're going to do, determine the concentration. So again, we're looking for concentration of acetic acid if 25 milliliters of it is required, 38.2 milliliters of zero point 0.1 molar NaOH to reach the equivalence point. So again, we're really just adding, okay? So we have acetic acid, which is HC2H3O2, that's acetic acid, plus NaOH yields NaC2H3O2, because acetate's a -1, sodium's a +1, and HOH. Now this happens to be balanced already, so it's again just a 1-to-1 mole ratio. We are told that it takes 38.2 milliliters of this. That is a concentration of 0.1 molarity to react with 25.0 milliliters of this. So again, I kind of recommend that you go ahead and convert these into liters. So this would be 0.025 liters. And then we're going to start with our 38.2, which we need to convert. So that would be my, that would give me 0.0382 liters. Or you could start off with your 38.2 and then show the dimensional analysis of dividing by 1,000. Either way would work. But now that we already have it in liters, I can do 0.1 moles of NaOH for every 1 liter, since that's the molarity. And you're always going to start with what you know 2 things about. That's what you start with. Then you know it's a 1 mole of NaOH for every 1 mole of HCl. Oh, not HCl. HC2H3O2. Sorry, it's acetic acid this time. Which should then give us moles of H2C2 HC. Let me just erase it. I didn't really want to erase it, but we'll just erase it. Because I am not writing right. It's okay. So then we have HC2H3O2. Okay. So we should get some number of moles. Then we have to divide it by the liters, which would be 0.025 liters. Again, your answer should be in 3 significant digits, and it'll be molarity of HC2H3O2. Okay, so get that written on your paper, then do a calculation in your calculator, and we can check. All right. Now, I think I'm going to skip the next example so that we can go ahead and finish the notes today. So go ahead and flip your page over onto the back. I will tell you, if you want an additional example, I do have one, and like I said, I'll go back just a minute. You can get this one. It's in my PowerPoint on Schoology, so if you want a third example, you can go back and look at it there. But I'm going to go ahead. Since I did 2, I think you guys should be okay with that. All right. So there are some different theories about acids and bases or definitions. So we're going to talk about those now. The first one that we're going to talk about is the Arrhenius acids and bases thought process. So AB theories 1 with example is where you're writing this. Now, I would write this pretty much word for word. Um, but I would, well, no, I wouldn't write word for word. So arrhenius acids are acids that contain hydrogen ions. They contain hydrogen. They ionize into hydrogen ions when you break them into solution. So really, things like HCl is an example of it. It breaks into hydrogen. It breaks into chlorine. It's pretty easy. Now, an arrhenius base is one that breaks into hydroxide ions when it's in solution. So that would be NaOH. It breaks into positive Na ions and OH minus ions. All right. Then our second theory would be the Bronsted-Lowry theory. And Bronsted-Lowry theory, you have two parts to it. You have the acid and the base, which are going to be your reactants. And acids are hydrogen ion donors. So for hydrogen ion, you could just write H positive to shorten it. Another way of thinking about it is it's a proton donor. Okay. And then a base would be a hydrogen ion acceptor or a proton acceptor. So if we have the equation of NH3 plus H2O, the NH3 becomes NH4, which means it gained a hydrogen ion. So since it gained a hydrogen ion, that would make NH3 the base. Now the H2O, when it went to the other side, now became just OH minus, which meant it lost a hydrogen, which means that it's the hydrogen ion donor. So the acid loses a hydrogen where the base gains a hydrogen. And remember, these are always going to be reactants. Okay? So we would classify the NH3 as the base and the water as an acid. Now on the flip side, we can also give the products actually a name as well. And the products of this same reaction would be called the conjugate acid and the conjugate base. Now these are your products. And this is the conjugate acid is the product that gained the hydrogen. And the conjugate base is the product that lost the hydrogen. Okay? So when I say that, so this was my base, so this became my conjugate acid. Then this was my acid, so this became my conjugate base. So really their conjugate is the opposite word. So the base gained the hydrogen, so that makes it my conjugate acid as the product. And the acid lost the hydrogen, so it became the conjugate base. All right. Let's do some examples here. So HCl, as it came over here, all right, did it lose or gain a hydrogen? Well, it lost a hydrogen. If it lost a hydrogen, then does that make it an acid or a base? Hopefully you said an acid, okay? Then, if you look at the H2O, it gained a hydrogen, so that makes this the base. That would make the chlorine a conjugate base and the hydronium a conjugate acid. All right? Probably ought to go ahead and delete my stuff there. So let me go ahead and delete that.
doesn't confuse you. All right. Then another one here. I have um, I have H2O, and H2O when it goes to the other side becomes OH, so it lost a hydrogen. Since it lost a hydrogen, it's an acid. And the hydroxide would be the conjugate base as the product. Now my acetate ion becomes acetic acid, so it gains a hydrogen, which makes it a base as the reactant and a conjugate acid as the product. Here, though, I have H2O and H2O. Well, if I look at the original H2O, it becomes H3O. So that makes it a hydrogen gain. So that's a base with a conjugate acid for the hydronium. And then the other water happens to be a base, or sorry, happens to be an acid, which makes the hydroxide a conjugate base. Okay. Now notice water was an acid in some of these, a base in others. It was an acid and a base in both of these. So just a starred vocabulary word would be amphoteric that you need to write in your notes. You can write it somewhere underneath the AB theory number 2 still, or you can write it really anywhere. Amphoteric means that it can act as both an acid and a base. Water is an example of this, of amphoteric. All right. All right. So our final theory is the Lewis acids and bases. Lewis acids and bases talk about acids as electron pair acceptors. Remember, you can write electron as E with a negative. And bases would be electron pair donors. So your example would be if we have H positive plus water becomes hydronium, then the H would be an acid because it's going to accept an electron pair, and the water would be the base. Okay. Another example would be AlCl3 plus Cl minus. The AlCl3 would be the acid because it accepts an electron pair when it becomes AlCl4 minus. And the Cl would be the base because it's going to donate its negative to the AlCl3. All right. So get those written down. Get at least one of your examples written down. And then I'm going to put the slide up that has all the common acids and bases names. I am going to, or it has their formulas. You should be able to figure out their names or learn their names, but I just wanted you to be aware of them so you'll be able to list them on the next screen. That's where the slide can stay after I flip to the next slide, and then we will be done. You'll need to work on your other assignments that you have. So these are your common acids and bases. You have HCl as hydrochloric acid. You have HNO3 as nitric acid. You have H2SO4 as sulfuric acid. You have H3PO4 as phosphoric acid. You have HC2H3O2, which is acetic acid. And you have H2CO3, which is carbonic acid. For your bases, you have NaOH, which is sodium hydroxide. KOH, which is potassium hydroxide, CaOH2, which is calcium hydroxide, MgOH2, which is magnesium hydroxide, and NH3, which is ammonia, which you already have in your notes somewhere. Okay? So this one can sit here. You guys can get it written into your notes, and have a good one.